Your phone is warm right now. Not because of the battery, not because of the screen. It's warm because it is thinking. Every calculation, every notification, every moment it spends remembering your name generates heat. And here's what no one tells you. That heat isn't a flaw. It's a confession. The universe admitting that thought has weight. In 1867, a Scottish physicist imagined a creature that could break that rule. A tiny being, sitting at a door between two rooms, sorting molecules one by one. Fast ones to the left, slow ones to the right. Creating order from chaos, energy from nothing. He called it a demon. For 150 years, the greatest minds in physics tried to kill it. And in failing, again and again and again, they stumbled onto a secret the universe had been keeping since the beginning. That information, the quiet stuff that thoughts are made of, weighs something, costs something, is something, as real as light, as unavoidable as gravity. And in 2024, a team at Cambridge gave that demon a body. Not in theory, not in simulation, in glass and light and molecules, pumped across centimeters by a principle that connects the heat in your hand to the fate of the stars. I remember the first time I understood that everything falls apart. I must have been 8 or 9. I'd spent an entire afternoon building a tower out of wooden blocks. A cathedral, I called it. And when I stood up to admire it, my elbow caught the corner, and it fell. All of it. In less than a second, an afternoon's work became a pile on the floor. And I remember staring at that pile and thinking, why? Why is it so easy to destroy and so hard to create? Why does the tower never build itself? Why does the mess never apologize? It seemed unfair, like the game was rigged before anyone sat down to play. It turns out, it is. There is a rule, perhaps the deepest rule in all of physics, that says the universe has a direction, a preference, a slope it slides down and never climbs back up. From order to disorder, from structure to dust, from hot to cold, from together to scattered, from known to forgotten. Scientists call this rule the Second Law of Thermodynamics, but you already know it. You've been living inside it your whole life. Drop an egg. It splatters. You have never, not once in all of human history, seen an egg unsplatter. A cup of coffee has never separated back into hot black and cold white. A campfire has never unburned. The smoke has never crawled back down into the wood. The reason is a quantity called entropy. Think of it as nature's measure of disorder, or more precisely, the number of ways something can be rearranged without anyone noticing the difference. Imagine shuffling a deck of cards. There's exactly one way to arrange them in perfect order, ace through king, suit by suit. But there are more than 8 times 10 to the 67th power ways to arrange them randomly. That's a number with 68 digits. So when you shuffle, you're not choosing disorder, you're just falling into the overwhelmingly more probable arrangement. Order isn't forbidden, it's just so spectacularly unlikely that the universe doesn't bother. And that is the second law. Not a commandment carved in stone, a probability so crushing, so absolute, it might as well be fate. But in the winter of 1867, in a candlelit study in Edinburgh, while the cold pressed against the windows and the fire ate itself alive in the grate, a man named James Clerk Maxwell sat down to write a letter. And in that letter, he asked the most dangerous question in the history of thermodynamics. What if you could cheat? James Clerk Maxwell was, by any measure, one of the greatest physicists who ever lived. Einstein kept a photograph of Maxwell on his study wall, alongside Newton and Faraday. Maxwell had already unified electricity, magnetism, and light into a single theory, a feat of imagination so profound it rewired civilization. Radio, television, Wi-Fi, the phone warming your hand right now. All of it flows from equations Maxwell wrote before he turned 40. But Maxwell had a restless mind, and in December of 1867, he sat down to write a letter to his friend, Peter Guthrie Tait. In that letter, he described something playful, almost mischievous. He imagined a being, small enough to see individual molecules. Not a god, not a spirit, just a creature with very good eyes and very fast hands. Picture two chambers filled with gas at the same temperature. The molecules are bouncing around randomly, some fast, some slow. On average, both sides are identical. There's no temperature difference, no energy to extract. The system is in equilibrium. Now picture a tiny door between the two chambers. And at that door, sitting in the dark between the molecules, a demon. The demon watches, patient, still. A molecule approaches from the right, a fast one, vibrating with heat. The demon opens the door, lets it through, closes the door behind it. Another molecule approaches, a slow one. The demon does nothing. The door stays shut. Fast ones to the left, slow ones stay right. One by one, molecule by molecule. The demon asks the same question 1 billion times. Are you fast or are you slow? And something impossible happens. Slowly, quietly, without anyone lifting a finger. The left chamber grows warm. The right chamber grows cold. A temperature difference appears where none existed. Order assembling itself from chaos. Without burning any fuel, without pushing any piston, without spending a single joule. And once you have a temperature difference, hot here, cold there, you have an engine. You can spin a turbine, generate electricity, light a city, all from a gas that was doing nothing a moment ago, but sitting in the dark. Think about what the demon has done. It has taken the most degraded form of energy in the universe, the random jostling of molecules, heat spread so thin it can do nothing, and it has concentrated it, organized it, made it useful, for free, forever. It has run time backwards. The second law says this cannot happen, not because it's forbidden by some cosmic rule book, but because it's so unlikely that all the time since the Big Bang isn't long enough for it to happen once. And yet here is a creature that does it casually, effortlessly, using nothing but knowledge. Maxwell didn't call his creation a demon. He called it a finite being, a creature that could play a game of skill with the molecules. It was Lord Kelvin who, 7 years later, gave it the name that stuck, demon. As if something that small and that clever must be up to no good. Maxwell wasn't trying to destroy thermodynamics. He loved thermodynamics. He was trying to understand where it broke, to feel along the wall for cracks. But what he'd created was a crack so deep it would take 115 years to seal. And the material that finally sealed it would turn out to be the strangest building material in the history of science. Not matter, not energy, information. To understand why Maxwell's demon kept physicists awake for more than a century, you need to understand what it threatened. The second law of thermodynamics isn't just a rule about heat and engines. It's the reason the past is different from the future. It's why we remember yesterday, but not tomorrow. It's why we age, why stars burn out, why every fire eventually becomes ash. Without the second law, there is no arrow of time. Without it, the universe has no direction, no story. Arthur Eddington, the astronomer who proved Einstein right by measuring the bending of starlight, wrote that the second law holds the supreme position among all laws of nature. He said that if your theory contradicts the second law, there is nothing for it but to collapse in deepest humiliation. And here was Maxwell's little thought experiment, sitting at its tiny door, casually suggesting that maybe, just maybe, there was a loophole. If the demon could work, then everything we thought we understood about energy, time, and the fate of the universe would need to be reconsidered. The entire framework of thermodynamics, the science that powers civilization, that tells us why engines run and why ice melts and why nothing lasts, would have a crack in its foundation. Scientists don't react well to cracks. Some tried to dismiss the demon. Others tried to build it. Most tried to find its fatal flaw. But for decade after decade, no one could. The demon sat at its door, sorting molecules, smiling, waiting. Its secret was hiding in the last place anyone thought to look. Not in its hands, not in its eyes, inside its memory. Leo Szilard was not the kind of physicist who waited for problems to come to him. He was Hungarian, brilliant, restless, the kind of mind that filed patents on particle accelerators and nuclear reactors before anyone had built them. In 1939, he would draft the letter, signed by Einstein, that warned President Roosevelt about the possibility of an atomic bomb. A letter that bent the course of the 20th century. But a decade earlier, in 1929, Szilard was wrestling with a different kind of danger. Not nuclear, informational. Szilard did what the best minds always do. He stripped the problem down to its bones. Forget billions of molecules, forget fast and slow, forget the demon's cleverness. Imagine the simplest possible version. One molecule, one box, one question. Now slide a partition into the middle. The molecule is on either the left or the right, 50-50. One bit of information. The smallest question that can be asked, left or right. Here's the trick. If you know which side the molecule is on, if you look, if you measure, if you learn the answer to that single binary question, you can attach a piston to that side and let the molecule push it as it bounces around, expanding to fill the whole box. That push does work. Real, measurable work. From one particle in a box, you have extracted energy. The amount? Exactly k minus t times the natural log of 2. A whisper of energy. A breath. But not nothing. And in principle, you could do it again, and again, and again. Forever. Szilard had built the smallest heat engine in the universe. And its fuel was not coal, not oil, not uranium. Its fuel was a fact. One bit of knowledge about one particle, converted directly into motion. But Szilard realized something else, something that would haunt physics for the rest of the century. He wrote, and this is the crucial sentence, that the demon must perform a measurement. And that measurement, he argued, cannot be free. Somewhere in the act of looking, in the moment the demon opens its eyes and learns left or right, a price must be paid. Because if it isn't, the second law is broken. And the second law does not break. Szilard didn't know exactly where the cost was hiding. He suspected it lived in the act of measurement itself, in the moment of looking. But he had named the three characters in the play that would eventually solve the mystery: measurement, information, and entropy. And with that, the hunt changed shape. The question was no longer, can the demon work? The question was harder, stranger, and more beautiful. What is the physical cost of knowing something? In 1951, a French-American physicist named Léon Brillouin picked up the trail where Szilard left it. And he asked a question so simple, it's almost embarrassing that no one had answered it before. How does the demon see? Think about where the demon lives. Inside a box of gas at thermal equilibrium. Everything is the same temperature. The walls, the air, the molecules, the demon itself. There is no contrast, no shadow, no outline. It's like being inside a fog made of heat. The whole space glows with the same featureless thermal radiation. Infrared everywhere. Everything the same temperature as everything else. The demon is blind. Unless it brings its own light. To see a molecule, to distinguish it from the warm background hum, the demon needs a flashlight, a source of photons with more energy than the thermal noise around it. Brillouin calculated what happens when the demon shines a light on a molecule to measure its speed. The photon hits the molecule, bounces back, and the demon reads the result. Information gained. But that scattered photon doesn't come back neatly. It ricochets, goes off in a random direction. The ordered photon from the flashlight has become a disordered photon, lost in the dark. The entropy of the light itself has increased. Brillouin did the math. The entropy increase from that scattered photon was at least as large as the entropy decrease the demon achieved by sorting. Debit and credit. The books balanced. The second law held. Or did it? Brillouin's argument was specific. It applied to one particular method of measurement, photons bouncing off molecules. But what if the demon was cleverer than that? What if it could measure without light? What if there were quieter ways to listen? The exorcism was incomplete. The demon had been wounded, but not killed. And so the paradox persisted for another decade, until a man at IBM, working on something that seemed completely unrelated, the fundamental limits of computation, stumbled onto the real answer. And the real answer wasn't about seeing at all. Before we meet the man who finally killed the demon, we need to understand a revolution that was happening in a completely different room. A revolution in the meaning of the word information. In 1948, a 32-year-old engineer named Claude Shannon published a paper that some consider the most important scientific paper of the 20th century. 45 pages, dense with mathematics. It appeared in the Bell System Technical Journal, and it was called A Mathematical Theory of Communication. It invented the world we live in. Every text message, every streaming video, every phone call, every bit of data passing through every wire on Earth runs on mathematics that Shannon wrote in that paper. Shannon asked a question that nobody had properly formalized. What is information? Not philosophically, not poetically, mathematically. How do you weigh a message? Here's the intuition. If I flip a fair coin, the result, heads or tails, carries one bit of information. You didn't know what would happen, and now you do. That surprise, that resolved uncertainty, is information. But if the coin is rigged, always heads, then flipping it tells you nothing. No surprise, no uncertainty resolved. 0 bits. Shannon showed that information is surprise. It's measured by how uncertain you were before the message arrived. The more the message changes what you know, the more information it carries. And the mathematical formula he derived for this looked familiar, eerily familiar, like meeting a stranger who has your mother's face. It looked like Boltzmann's entropy, the thermodynamic formula for disorder. Same structure, same logarithm, same shape, different letters, different units, but the same bones underneath. And here's where one of the most famous conversations in the history of science comes in. Shannon wasn't sure what to call his formula. He considered information. He considered uncertainty. The mathematician John von Neumann, perhaps the greatest intellect of the 20th century, told Shannon, "You should call it entropy, for 2 reasons. First, your uncertainty function has been used in statistical mechanics under that name." And then, von Neumann reportedly added, "Second, and more importantly, nobody knows what entropy really is, so in a debate, you will always have the advantage." Whether the story is apocryphal or not, the name stuck, Shannon's entropy. And the parallel between information and thermodynamics, which Maxwell had hinted at, Szilard had glimpsed, Brillouin had touched, was now written in the mathematics itself. Not analogy, identity. Information and entropy, 2 names for the same thing. Knowing reduces uncertainty. Forgetting increases it. And between those 2 facts, between knowing and forgetting, between order and chaos, the universe keeps its most careful accounts. But the deepest connection, the one that would finally, permanently kill the demon, was still 13 years away. Rolf Landauer was a German-American physicist working at IBM. He wasn't thinking about demons, or entropy, or the arrow of time. He was thinking about something practical, something engineers complained about every day. He was thinking about why computers get hot. This was 1961. Computers filled entire rooms and consumed enormous amounts of electricity. Most of that electricity became heat, and Landauer wanted to know, was all that heat a failure of engineering? Could you build a computer that ran perfectly cool? No waste, no warmth, nothing lost. He began with the smallest possible question, a single logic gate, an AND gate. 2 inputs, 1 output. 2 bits go in, 1 bit comes out. Landauer noticed something that seems obvious once you see it, but that no one had seen before. 2 bits enter, 1 bit leaves. A bit has gone missing. The output alone cannot tell you what the inputs were. An AND gate that outputs 0 could have received 0, 0, 0, 1, or 1, 0. 3 histories compressed into 1. Information has been destroyed. A fact about the world existed, and now it doesn't. And Landauer argued, with the calm certainty of a man who knows he's right, that this destruction has a physical cost. He calculated the minimum amount of energy that must be released as heat, surrendered to the universe, lost forever, when 1 bit of information is erased. K, Boltzmann's constant, the conversion factor between the world of molecules and the world we can touch. T, temperature, how warm the environment is, how agitated the molecules around you already are. And ln 2, the natural logarithm of 2, because a bit has 2 states, and erasure collapses them into 1. The mathematical weight of a binary choice. At room temperature, that works out to about 3 × 10⁻21 joules, an almost inconceivably small number. A whisper of warmth, the faintest breath of heat. But not 0. This is Landauer's principle, and once you understand it, you can never un-understand it. Erasing information, forgetting, is not free. It has a cost, a physical, measurable, thermodynamic cost. Every time a bit is destroyed, a tiny quantity of heat must escape into the environment. Not because of bad wiring, not because of friction or resistance or imperfect engineering, because of the structure of reality itself. The universe charges for forgetting the same way it charges for everything else. Information is physical. Think about what that means. We imagine information as weightless, abstract, a thought in a mind, a word on a page, ones and zeros floating in some ethereal digital space. But Landauer showed it isn't ethereal at all. Information obeys the same laws as a stone falling, a star burning, a river running downhill. It has weight, thermodynamic weight. It costs energy to create. It costs energy to destroy. And between creation and destruction, it exists in the physical world as surely as light. When you remember someone's name, that memory has a physical cost. When you forget it, the forgetting generates heat. Not metaphorically, actually. The universe gets a little warmer every time a fact disappears. Landauer didn't immediately connect this to Maxwell's demon. That connection would take another 20 years. But the key insight was in place. Information is not something that floats above the physical world, looking down. Information is in the world, made of the same stuff as everything else, subject to the same laws, paying the same taxes. Charles Bennett was also at IBM, and in 1982 he published the paper that finally killed Maxwell's demon. Not wounded it, not weakened it, killed it. Bennett's genius was to look in the direction no one else was looking. For 115 years, every physicist who'd wrestled with the demon had stared at the same moment, the measurement. They assumed the cost was in the looking, the act of a demon opening its eyes and learning a molecule's speed. Szilard thought so. Brillouin thought so. Bennett showed they were all wrong. Measurement can, in principle, be done for free. No thermodynamic cost at all. The real cost isn't in learning, it's in forgetting what you've learned. Think about the demon's life. It measures a molecule, records the result in its memory. Fast. Opens the door, closes the door, measures the next molecule. Slow. Door stays shut. Next molecule. Fast. Door opens. Next, next, next. 1 bit, 2 bits, 100 bits, 1,000,000. The demon's memory fills like a jar filling with sand. Grain by grain, molecule by molecule, it accumulates a record of every measurement it has ever made, every molecule it ever sorted, every door it ever opened, an ever-growing ledger of the gas's entire history. And memory is not infinite. Eventually, the tape runs out. The jar is full. The demon has no room left to record the next measurement. It has to erase. It has to forget. And that is where the bill comes due. By Landauer's principle, every bit the demon erases radiates at least kTln2 of heat into the universe. That heat increases the entropy of everything around it. And Bennett proved, line by line, equation by equation, with the precision of a watchmaker, that the total entropy increase from erasing the demon's memory exactly matches the entropy decrease the demon achieved by sorting. To the last fraction, to the last molecule, the universe's books balance. The demon can sort, but it must remember. And when it forgets what it remembers, as it eventually must, the heat it releases gives back everything it gained. Every molecule sorted, paid for by a molecule's worth of heat. Every bit of order purchased with a bit of disorder. The demon's fatal flaw isn't in its eyes. It's in the space between its ears. It can see perfectly well, but it cannot forget for free. And forgetting is the price of continuing. No free lunch, no free thought, no cheating the second law. Because the universe doesn't just charge for energy, it charges for knowledge. And forgetting is the receipt. After 115 years, after Maxwell's letter and Szilard's engine, and Brillouin's photons and Shannon's formula and Landauer's principle, the demon was dead. Killed not by force, but by accounting. The universe simply presented the bill. And the bill revealed something more profound than the paradox it settled. The boundary between physics and information isn't a boundary. It's a mirror. Thermodynamics and information theory aren't two sciences that happen to look alike. They are one science, one truth, seen from two sides. The laws that govern engines and stars and the cooling of coffee also govern thoughts, memories, and the act of forgetting your keys. All the same ledger, all the same accounts. But this was all theory. Beautiful, complete, logically airtight theory. No one had ever measured the cost of erasing a single bit. No one had held the demon's bill in their hands and read the number. Until the 21st century. Lyon, France, 2012. A team led by physicists Antoine Brillouin and Eric Lutz set out to do what had never been done. Hold a single bit of information between their fingers, and measure the heat released when they destroyed it. Their apparatus was a small miracle of precision. They trapped a silica bead, 2 micrometers across, smaller than a red blood cell, smaller than a wavelength of visible light, in a beam of laser light. By shaping the laser, they created a double well potential, 2 tiny valleys separated by a hill of light. The bead could rest in either valley. Left valley, 0. Right valley, 1. 1 bead, 2 positions. 1 bit of information, held in place by nothing but light. To erase that bit, to force the bead to a known position regardless of where it started, they lowered the barrier between the valleys and gently tilted the potential, nudging the bead to one side. Then they raised the barrier again. The bead was now always in the same well. The bit was gone. And they measured the heat. Cycle after cycle, erasure after erasure. Hundreds of times they destroyed a bit and measured what the universe charged for it. When they erased slowly, patiently, giving the system time to breathe near equilibrium, the average heat released settled toward a number. kT times the natural logarithm of 2. Landauer's number. The price Landauer predicted in 1961, sitting at his desk at IBM, thinking about logic gates. 51 years. That's how long it took between the prediction and the measurement. Half a century from equation to confirmation. From "this must be true" to "this is true." The connection between information and thermodynamics was no longer mathematics. It was physics. Real. Measured. Confirmed in a laboratory in France, 1 bead at a time. The paper was published in Nature, and it sent a quiet shock through physics. Not because the result was surprising, most physicists expected it, but because of what it meant. If erasing a bit really does cost energy, if forgetting really does generate heat, then information isn't a metaphor for something physical. Information is physical, and the ledger is real. 2 years later, in 2014, a team in Finland, led by physicist Jukka-Pekala, went further. They built an actual, functioning Maxwell's demon. Not a thought experiment, a machine. Their demon was a single electron device, a transistor cooled to within a breath of absolute zero, where individual electrons could be tracked like animals on a savanna. 1 electron at a time. The system worked exactly like Szilard's engine. A single electron in a box. Measure which side it's on. Use that information to extract work. And it worked. The team extracted almost exactly kT ln2 of energy per measurement. The maximum. The Szilard limit, realized in silicon and superconductors. But they also confirmed the cost. When the demon's memory was erased, when the record of the measurement was wiped, the extracted energy came back as heat. Every joule gained returned. The net gain, 0. A year later, the same group built something more remarkable still. A demon that ran itself. An autonomous device that measured, extracted, sorted, all without a human hand touching it. They watched one part of the circuit cool down. They watched the demon's memory heat up, and the total entropy of the combined system increased, exactly as Bennett had calculated 30 years before. For the first time in history, Maxwell's demon was running in real hardware. Sorting, remembering, paying, and the second law held, down to the last electron, down to the last bit. And then, 157 years after Maxwell's letter, came the breakthrough that made the invisible visible. A team at the University of Cambridge, led by chemist Jonathan Nitschke, published a paper in Nature Chemistry that announced something no one had achieved before: a macro-scale Maxwell's demon. Not electrons, not beads in laser traps, molecules, pumped across centimeters of physical space, distances you could measure with a ruler. Their system was, at its heart, beautifully simple. A U-tube, 2 arms filled with a molecular solution, connected at the bottom through an aqueous layer containing something called a coordination cage, a molecular structure shaped like a tiny tetrahedron, a cage small enough to hold a single molecule. The cage was the demon, and light was its door. Here's how it worked. The cargo, a molecule called orthofluoroazobenzene, comes in 2 shapes. Think of it as a key that can be straight or bent. In its straight form, it fits inside the cage. In its bent form, it doesn't. When the team shone green light on one arm, molecules there switched from straight to bent. They no longer fit in the cage. Expelled, they drifted through the liquid to the other arm. In the other arm, violet light bent them back to straight. The cage grabbed them, held them, and so molecules accumulated, migrated, concentrated, pumped from one side to the other by 2 colors of light and the geometry of a cage too small to see. 20 days. That's how long it ran. And at the end of 20 days, a measurable concentration gradient had formed. More molecules here than there. Order from disorder. A hill built from flatness. Exactly what Maxwell imagined in his Edinburgh study, in candlelight, in 1867. And the second law held, because the light was the fuel. Every photon that switched a molecule's shape carried energy into the system. The cage was the demon, and the photons were the price of its sorting. No violation, no loophole, just physics, working exactly as Landauer and Bennett said it must. But what made this result sing wasn't just that it worked. It was the scale. Every previous demon had operated on invisible things, single electrons, single molecules, beads smaller than bacteria. This one moved material you could watch, across distances you could point to. A demon made of cages and light, sorting molecules across a glass tube in a chemistry lab in Cambridge. 157 years after a letter between friends, the thought experiment had become a thing you could hold in your hands. Not a violation of physics, a love letter to it. Now, let's follow this thread and see where it leads. Right now, the data centers that power our digital world consume roughly 2% of all the electricity on Earth, and most of that energy becomes heat. When you ask an AI a question, the chips thinking through your request generate warmth. When your phone stores a photo, transistors dissipate energy. When a computer deletes a file, any file, even a file you never meant to save, heat is released. Modern transistors operate about 1,000 times above the Landauer limit. There's room to improve. Engineers improve every year, shrinking transistors, reducing waste, pushing closer to the floor. But there is a floor. a basement, a bottom beneath which no technology, no matter how advanced, can ever descend. Erase one bit, pay KT lon 2, that's the rent, and the landlord is the second law. For a single bit, the cost is nothing. For the trillions of bits a modern processor erases each second, it adds up. For artificial intelligence, models with billions of parameters, trained on oceans of data, answering millions of questions, it becomes a question not of engineering, but of physics. There may come a day when the limiting factor in computation is not the speed of our chips or the elegance of our code, but the thermodynamic price of forgetting. When Maxwell's demon, long dead, long exercised, still sets the boundary on what minds can do. Silicon or biological, engineered or evolved, all minds, all bound by the same law. But the thread doesn't stop at computers. It runs further, much further. In 1973, the physicist Jacob Bekenstein, a student of John Archibald Wheeler, discovered something astonishing about black holes. Their entropy, their disorder, their information content, is proportional to the area of their event horizon, not the volume, the surface. As if everything that has ever fallen into a black hole, every star, every planet, every photon, every bit of information, is written on its skin. A cosmic library, stored not in the volume of the darkness, but on its edge. Each tiny patch of the horizon, one Planck area, roughly 10 to the minus 66 square centimeters, holding approximately 1 bit. This is called the holographic principle, and it whispers something extraordinary. The universe may store its information the way a hologram stores an image, not in the volume, on the boundary, on the skin of things. Wheeler, who coined the terms black hole and wormhole, who taught Feynman, who shaped the physics of the 20th century, looked at all of this and saw a pattern so vast it swallowed everything else. In 1989, he proposed what may be the most ambitious idea any physicist has ever spoken aloud. He called it from bit. Every physical thing, every particle, every force, every ripple in space-time emerges from information. Bits. Yes or no answers to yes or no questions. The same binary choices Szilard imagined in 1929. The same bits Shannon measured in 1948. The same bits Landauer priced in 1961. Not information about reality. Information as reality. Maxwell's demon didn't just connect thermodynamics to information theory. It opened a door, a small door, between two rooms, and on the other side was a view of the universe where matter, energy, space, and time are all woven from a single thread. And the name of that thread is the oldest, simplest thing in the world. A bit. A choice. A yes or a no. Repeated enough times, in enough patterns, to build everything that exists. There's something beautiful about the shape of this story. It started with a letter between friends, two Scottish physicists writing to each other about molecules, and one of them imagines a creature at a tiny door. A playful idea, almost a joke. And from that joke, through a century and a half of thinking, across continents and languages and generations, came a principle that connects the heat in your phone to the information on the surface of a black hole. A thread that runs from a candle on a desk in Edinburgh to the edge of the observable universe. The demon was never the enemy. It was the teacher. It taught us that the second law of thermodynamics is bigger than we thought. It doesn't just govern steam engines and melting ice. It governs thinking, knowing, forgetting. The same law that says your coffee will go cold also says your thoughts have a thermodynamic weight, that every memory you form warms the universe by a whisper, that every fact you forget releases a breath of heat into the dark. It taught us that measurement has a cost and forgetting has a price. And between those two costs, the universe runs its accounts with a precision that makes our best accounting look like crayon on a napkin. It taught us that information is not a ghost, not an abstraction, not something that exists above or outside the physical world, looking in through the window. Information is the world. The boundary between mind and matter, between knowledge and energy, between the abstract and the concrete, is thinner than a photon, thinner than a thought. It may not be there at all. And perhaps most wonderfully, this story taught us something about ourselves. A thought experiment in a letter in 1867 led, through Szillard's engine and Brillouin's photons, and Shannon's formula and Landauer's principle and Bennett's resolution, to experiments that confirmed predictions down to individual electrons, down to individual bits, down to the whisper of heat released when a single fact is erased from a single bead of glass. The human mind, 3 pounds of matter running on 20 watts, barely enough to light a dim bulb in an empty room, traced that thread. From a demon to a principle, to a law, to a number on a graph. From imagination to understanding. From question to answer. That's not just physics. That's the most improbable thing in the story. That a brain made of atoms could figure out the rules the atoms follow. The candle on this desk is converting order into disorder, wax into carbon dioxide, structure into heat, entropy increasing with every flicker, as it has since the flame was lit, as it will until the wax is gone. And the light it throws, the photons striking these pages, the signals racing through neurons as I read the words, all of it has a cost. Every thought I think warms the room by an amount too small to measure and too real to deny. That's the demon's final lesson. There is a price for knowing. For every thought, every memory, every moment of understanding. The universe charges for it all. In heat, in entropy, in the slow unwinding of order into chaos. And we pay it. We pay it gladly, because the alternative, the only alternative, is the dark, the equilibrium, the state where nothing is known and nothing is felt, and the molecules bounce in silence forever, without anyone watching. And in a universe that keeps its accounts in information, knowing is the most expensive thing there is, and worth every bit. This is Cosmic Canvas, where we weigh the weightless. Until next time, remember that knowing costs something. Pay gladly. It's the only currency that matters.